Welcome to NASA's VIPER Moon Rover Robot Build Watch Party. I'm your host, Erica Hengaski, and we're super excited to have you join us today for an exclusive behind-the-scenes look at VIPER as it's being built. Today we have two VIPER mission experts that will be answering your questions coming in from the chat. Let's meet them. Welcome.
Thank you. Good to be here.
Yeah, absolutely. Tell us your name and what you do for the VIPER mission.
Sure. My name is Tony Colaprete. I'm the lead project scientist, which basically manages the entire science team, helps with designing the initial science requirements and the measurements we need to make, and leads the planning, the science planning, in terms of what we're going to be doing on the moon when we get there.
Absolutely. And can you tell us your name and what you do for the mission?
I'm Dan Andrews. I'm the project manager for VIPER, which means in charge of the entire project's development and mission execution ultimately.
Awesome. And we have a special guest today with us, Scott Manley. Hey, welcome, Scott.
Hello. Yes, I'm Scott Manley, and you may know me from the internet, where I talk about rocket science and play video games and possibly do both at the same time. And I'm delighted to be here in the presence of some real scientists.
Awesome. We're excited to have you guys here. It's going to be a fun show. Why don't we start with what the VIPER mission is and what are the priorities?
Sure. You want me to take that?
Yeah, go ahead.
Okay. So the VIPER mission is it's a lunar reconnaissance resource prospecting mission. Mm-hmm. And what does that mean? It means it's going to the south pole of the moon, or in a region very near the south pole of the moon, and it's going to do what somebody would do on the Earth if they were looking for resources, mm-hmm. like copper ore. It's going to drive around making measurements, prospecting, and mapping the surface, the composition of the surface, the environment, like temperatures, mm-hmm.
the
soil mechanics, things like that. All the various things that are important to understanding where water might be on the south pole of the moon. It's not necessarily going there to find water. Mm-hmm. It's going there to actually make very systematic observations that actually let us understand and build models that help us predict where water might be for future follow-up missions.
Amazing.
Yeah.
And that's a great summary. Why don't we take a look at the clean room where VIPER, NASA's moon rover, is being built. Can you tell us a little bit about what we're seeing here and where it's being built in?
Yeah, so VIPER is being built at NASA Johnson Space Center. The physicality of the rover is being built there, thermal systems, mechanical systems, all the rest. And then rover flight software is being developed here at Ames. So we have a really nice partnership between these two NASA centers. For those who have been following along, you've been seeing all this progress. This has really been a fun feed, even for those of us on the team, mm-hmm. To see the rover coming together. So for those of you who've seen it, you understand what's under the MLI curtain there, the multi-layer insulation curtain. But what's inside are all of the electronics and thermal management systems required to keep this rover alive through a very challenging mission that we have ahead of us. And that silver foil looking stuff around the side, that MLI, is the final layer for the rover before we put on the solar arrays that'll be going around the three of the sides of the rover. So we're getting near the end. I think by last count we're about 88% complete.
Wow.
by hardware. So.
And when is it expected to be complete?
It will be done with the build phase in probably middle May, mm-hmm. and then that's not the end, that's just the beginning, because then we got to go prove that this rover can do what we thought it was going to do. And so we go into a bunch of different tests. So there's Dave. A bunch of different tests and environmental tests. Mm-hmm. The moon is a really harsh place, in many ways worse than Mars, and so we have to go see if the rover can endure that, and even more importantly, understand the personality of what we built. Mm-hmm. We hope it does what we wanted it to do, but even more important is that we understand whatever it is that it does, because then when we're on the surface and we see something that's maybe not quite what we expected, mm-hmm. we know what this can do, so maybe it's environmental, maybe something happened, maybe there's a discovery happening. So it's really important this next phase.
Is someone waving?
Yes,
Yeah,
we've got waves from the build.
Awesome. And what has been like a highlight for you for the build here? Any highlights?
Boy, so many, actually. And as Dan described, the entire project has this feed, and it's often very difficult for me to turn it off and get to the meeting that I'm supposed to be at, because it's just watching it come together. Actually, can't come together so quickly. You know, there's this build-up, of planning, and then there's some issues you have to work out. But once those issues got out of the way and fixed and everything was there, this integration team down here just rock and rolled. I mean, they put this thing together quickly, and you know, so far very successfully, which is great. You know, knock on wood. And I guess when it first started out, you can tell it was what it was going to be. It just looked like it kind of exploded something there with it had blankets and wires and harnessing. You know,
wires.
Yeah,
oh my God, the wires.
The wires.
All the harnesses.
300 feet of some ridiculous number of wiring in it. But I think once, for me, once one of the panels, there's like 4 panels in there that build up the sides. One of them has an instrument on, Nervous, it's called, that I'm the lead for. And it has fiber optic cables, fiber optic bundles that go from a spectrometer on that panel down to the belly pan where it looks out of. And that was a very scary operation for the entire Nervous team, because those fiber optic cables, they're rigid, they're in a rigid container. But if you bent that at all, they would break. Oh. And so they developed this lift scheme where they put the panel on and mated basically the 2 fiber optic cables coming up into the spectrometer just very delicately, and it went perfectly. So as soon as they did that, they swore they'd never take it off again, and that was a highlight for me. That was like, okay, amazing. Good, we're past that. Yeah.
So you built out a lot of the components with harnesses before they go into the clean room, right?
Yes.
You know, you're not putting together these tiny boxes. These have been built elsewhere, and it comes in as a kit, basically, and then this is final assembly.
It varies a lot by the particular system. You know, you go into this trying to make sure that the subsystem level, you know, thermal system or a wheel module system or a driver system, that they all work before you get to this point. Because if you discover here that it doesn't work, man, you have a lot of backtracking to do, and that'll cost you time. And so we tried to test as much as we could in advance, but of course under schedule pressure, some things you had to just go ahead and put in and test them. One of the things that happened, I don't know, I think it was probably 2 to 3 to 4 weeks ago, there was a span there where we were doing a lot of channelization tests. That's one of the things, well, the terms that we use for checking out to make sure that all of those harnesses that you built and the pins that they connect through actually are proper. So when you command that this wheel should move in this direction, does it move in the opposite direction, or does that wheel move instead? Sounds really basic, but you've got to check all that out, and that's the process of channelization. And then very recently, we were in there doing what's called metrology, and there's this big arm device that was out there, and it's taking channelization to the next step. You now know that the wheels are correctly connected and that they spin the correct direction. You know that the pan tilt system up on top, which moves the cameras around and the antennas, you know that they're moving properly, but are they moving accurately?
Yep.
And so you need to actually move it around and take measurements and say, okay, we got within this tolerance, okay, move it back, It's very tedious, but you need to figure this out as soon as you can so that if there's any issues, you can address them.
Yeah, I mean, it seems basic, but I mean, I've seen rockets that failed for that exact reason. Right, that things were misconfigured or misconnected.
It's a fun thing to point out here. Right now, you can see one of the engineers up and inside the rover. They actually have certain individuals designated for certain roles and activities just based on their size, even their hand size.
Oh, interesting.
The thing is built like an onion, and meaning there's things in the middle there that were put on first, and then you build around that. Just the nature of the design, and some of those places you have to reach in still and connect things, do some tightening of bolts or whatever else, and they have specialized custom tools built to do it sometimes, and sometimes you just need the right person who can actually reach in there and,
You have
and
job ads for people with long arms.
Exactly, right. Yeah.
It's funny, is that's not so surprising in like the plumbing industry, electricians. It's all the same reason. Just this is a lot more expensive.
Yes. This is all built in a clean room, but you're obviously planning to take this to the moon, where the dust environment's going to be completely different. But I'm presuming this is all going to be sealed as much as possible against lunar dust intrusion, right?
Yeah, and we've actually done testing very early on in the design on, for example, all the mechanism that supports the wheels down here. It's 4 separately steerable wheels, 4 separately controllable suspension systems, and so there's a lot of mechanical movement, and it's really close to the soil.
Yeah.
So that just feels like a nightmare. Well, we have socks that actually go in there and protect all of those joints. But the soil on the moon, because it's basically all just cracked rock that's just cracked and recracked through impact gardening and all the rest, it's sharp shards, and Apollo astronauts and others have already confirmed the same thing. So what about the wear on the sock? How long can it last? Under what conditions? All of these things we had to test in advance to get to the design that we're ending up with.
That's wild.
You mentioned the Nervous instrument. We can't see it right now, but can you tell us a little bit about it?
Sure. The Nervous instrument is one of 2 instruments that are on what's called the belly pan, the bottom of the rover, and are looking out the hole where the drill actually lowers through when we were drilling. It sees the surface under the rover at all times, these 2 instruments. Nervous stands for the Near Infrared Volatiles Spectrometer System. And I gave it that unfortunate name very early on.
You did it.
Hard to,
You
say.
didn't stumble on your own acronym.
I thought at the time it would be pronounced nerves or something cool like that. And someone else said, "Is it nervous?" I'm like, "Sure, it's nervous." So what Nervous is it's actually a system of sensors, of instruments. It's not just one. It has a near-infrared spectrometer. Spectrometer's a device that separates light into its various colors. And we're looking at wavelengths that the human eye can't see. They're wavelengths a little bit longer than what we can see in the near-infrared. But at those wavelengths, those colors, a lot of volatiles like water has very distinct fingerprints. And so with that spectrometer, we can actually see water ice, water vapor, CO2 ice. We can understand the composition of the lunar soil itself, the mineralogy that's in it. So as we're roving along and it's looking at the surface, making those measurements. It also then has a camera that is a normal color camera. It operates from the ultraviolet to the near infrared, and it's taking high resolution images, resolutions as good as 100 microns per pixel, so very, very high resolution. And it can do that in 7 different colors. So it's actually doing high resolution composition measurements. And it also provides the context for that spectrometer I just mentioned, the near infrared spectrometer. And then the last thing it does is it measures surface temperature. And that was, there was really 2 reasons to measure the surface temperature. Is in some places on the moon, the surface is warm enough that the thermal energy coming off can influence the near-infrared spectrum, that the colors we're trying to observe. So we wanted to measure it and be able to correct for it. But more importantly is we wanted to know what the surface temperature was. What was the temperature of the cuttings? It also looks at the cuttings piles from the drill. We didn't want to get into a situation where we are exploring a location, drilling in a location that is cold, we think is cold enough from our models to be able to retain water ice, and we see nothing. And it's, wow, it's dry, there's no water. So we didn't want to be in a situation where we came up negative for water, but didn't know the temperature. We only knew what the model predict was. That would be like, well, what if the model was wrong? Oh man, maybe it was. So we said we better measure the temperature while we're doing the exact measurement for the water content. So this will tell us exactly what that temperature is. Is it indeed cold enough to hold water? And if it says yes, and we don't see water, that's a really important finding. But if we see no water and we go, oh no, it's actually only minus 200 degrees centigrade. It's too warm for water. So yeah.
I mean, yeah, that's a big thing about this drill. It's not the first drill to go to the moon, but it's the first time we'll be able to look at the stuff from the drill as it comes out
up,
of the
yeah.
moon.
Yeah, the other instrument down there is a mass spectrometer, so it's looking at gases, and it breaks up the gases into, or it can measure the molecular weight of each of those gases, so it can tell you, yes, that is water, or that's CO2, or that's so the two work hand in hand. One's looking at the solid state primarily, like ice, and then the other's looking at it in gas as it comes off. And that's, as you point out, really important to look at it in real time as those cuttings are coming out, because volatiles don't want to stick around for long. No.
Well, we're getting a lot of questions from the audience. If you're just tuning into the show, this is a great opportunity, great time to ask your questions and comments for the VIPER experts. Let's see, we have here. Let's see. How many teams of people and professions does it take to build a rover?
Wow, so that's actually a great question, because I think there's a lot of misunderstanding about that. You figure, you look at this, and it's clearly engineers and scientists, and it is, but it's so much more than that. This is a big endeavor, and so it requires many different disciplines of engineering, many different disciplines in the science community. It requires people who can do procurements, people who can do management of resources, funds, HR, just on and on, because there's a total, it varies in time over the course of the project, but you have maybe more than 300 people at any given moment in time who are working on this, and it's all kinds of disciplines to enable the project to move forward.
Awesome. Here we have another question. How many, if any, experiments will your rover be able to perform?
Great question. And over the course of the mission lifetime, we will visit. We will go to places we call science stations. So as we drive along, we're driving from science station to science station. A science station has been predefined by the science team. It's an area that has certain attributes about it. It's either really cold, or it's in between cold and hot, or there's a large crater there. And then we plan a number of science activities within that science station. Everything from, for example, taking a camera panorama. That's one of the very first things we do at every science station, just to get our bearing, is we take a 360-degree set of images that are stitched together to make a panorama. We've seen these from the Mars missions often. And we actually use that to help understand where we're going to go next and drive next. Often in a science station, we'll make more of these panoramas depending on how things go. Then within the science station, we do a lot of driving. It's a rover meant for driving. This rover is actually meant to cover close to 30 kilometers over the course of its lifetime, which is maybe 5 months. If you compare that to a Mars rover, where they're approaching maybe 20 or 30 kilometers over the course of 5 to 10 years. So we drive in real time, quick, really fast.
Yeah, it's one of those funny things where we drive half a mile an hour at top speed, which feels very slow to us, but in rover speak, that's like 4 times faster than any of the Mars rovers or anything else, and it's because we have so much ground to make. We got to worry about the lighting conditions, which is how we're powered.
Yeah.
Yeah, I mean, it is fascinating. You guys, I mean, a lot of people don't realize this is going to the South Pole, and you have sunlight a lot more, but you still have some shade, and you have to get from one safe haven to the next one in the time allotted to you. You have this very strict plan. You want to talk about how you planned that?
Yeah, exactly. That's a great point. Is that because of the low sun angle over the polar horizon, it never gets about 6 degrees over the horizon. Those shadows do sweep around very quickly. They actually, the shadow front moves at about the same speed as a rover.
So you're chasing, or the shadows are chasing.
The shadows are chasing us.
Shadows.
Exactly. It's really terrifying. So it takes tons of planning. We've developed all kinds of planning tools to, using terrain models, predict where those shadows are and how they're moving. And so we can drive through the corridors of light. And there are instances where we call them choke points, where the shadows come in really close and they're to either side of you, maybe 20, 30, 40 meters. and you're like,
Wow.
I've got to get through this. I've got 2 hours to get through it before they collapse on me. It's all considered. It's we design it with margin. Usually we try to keep the margin up at actually 2 days of margin to any shadow front, but that all has to be thought of ahead of time and planned. And then the science station, it's all planned. Some of the other activities we do is drilling. We have 3 drill sites in each science station, down to 1 meter. It takes us about 5 to 6 hours to drill to 1 meter, so that's not very fast. But we go down in 10 centimeter bites, we call them. 10 centimeters down, bring it back up, look at what we got, go down another 10 centimeters, bring it up, see what we got. So, yeah, that's all scheduled, and we have to keep to that schedule, otherwise the shadows will get us. Yeah.
To be clear, we have batteries.
Yes.
Yep.
So we can tolerate going into shadow, whether it's local terrain shadow or something bigger. But if the max that we can handle is on the order of 50 hours, and that's when we're in basically hibernation mode, where we're using as little power as we possibly can. If we're actually doing stuff, that 50 comes way down. So we can tolerate interim shadows, but we need to get back on the sun and be power positive, as we call it, as often as we can.
Yeah, we go purposely into a permanently shadowed region, right? So that's a region that has not seen sunlight for maybe 2 billion years. Wow. And that's some of our science stations are deliberately planned in these shadowed areas, and we get about 9 hours with all of our instruments. We do a double dip because that 9 hours isn't enough to get the driving we want to get done, the mapping, and the drilling. So what we actually do is we go in, we drive around and map it, we come back out, recharge, and while we're recharging, we're deciding actually where we want to drill, and then we go back in and drill.
So I have a question about an interesting shadow event. We are looking at a solar eclipse about a week from now, but if my math is right, you should be on the moon when there is a lunar eclipse. Do you have any special plans for that? So you'll be seeing the Earth blocking out the sun.
No, but we will.
You will have plans?
Yes, absolutely.
I hope you get some good photos.
Those eclipses are actually very important, not just cool, but very important scientifically. The Lunar Reconnaissance Orbiter, which is an orbiter that launched with LCROSS back in 2009, often takes advantage of those eclipses and makes measurements from orbit while in eclipse, because it gives you a very unique vantage point to actually measure how the surface temperature varies with shadow and how the reflectance changes and things like that. So it is a real opportunity we should take advantage of.
We have a question here from a viewer. How different is a moon rover from a Mars rover?
Well, I'll start that one, I guess.
You do it.
First of all, when you look at the rover, when you look online at our videos, when you look at this model, any of our imagery, it's pretty clear this is a very different kind of rover than you're used to. Instead of 6 wheels and what's called a rock or bogie arrangement, we have 4 wheels. Our 4 wheels are independently steerable. They're also independently controllable from a suspension point of view. To start at the high level, the basic premise is the way we have to move, the speed we have to move, and all the constraints we have force us to make a different kind of rover than what you're used to. Just to show how sophisticated the rover has to be, the rover has to move in a traverse that matches our science needs, so that's pretty clear. So you're moving this way, you're moving that way. That's fine, we know how to do that, moving the wheels and so forth. However, we want to, as you just heard, we want to keep the solar rays on the sun. And ideally, we keep them on the corner, one of the 2 corners on the back on the sun. So 2 solar rays are lit because we get maximum power generation that way. So we're going this way. Sun may be in a not so good position, so we could actually change the orientation of the rover, what's sometimes called crab walking, change the orientation of the rover so it's on the sun. The rover's going the direction we need to go for science. Then the cameras are looking out ahead, separately controlled from all of that. As we're going up and over terrain, the cameras are having to cancel the body movements of that. And at the top, up here, we have a highly directional high-gain antenna that has to look back at Earth and send all this data back to Earth. And it's compensating for the motion. So it's incredibly sophisticated in order to pull off this mission the way that we've laid it out. It also brings some additional capabilities that nobody's seen before. And again, I really encourage people to go look at videos on YouTube and so forth, because Since we can independently control the suspension system at each wheel, we have the ability, for example, if we're going into maybe a permanently shadowed region or an area of low consolidation soil where we could actually sink, potentially, we have the ability to actually manipulate our wheels and pull ourselves out on 3 wheels and set ourselves back down, because we can independently control them and move our what's called center of gravity around. We then took that to an extreme, this is where the videos come in, and started wondering, well, what if we just get stuck? We've done lots of testing up at Glenn Research Center in Ohio, and they have something called a sink tank, and it's appropriately named. It's not representative of what we expect lunar soil to be for the locomotion here. Instead, each of the grains of sand are spheres, so they just slip by each other. Every rover that goes across it immediately sinks to its belly. When we put ours in, immediately sank to its belly as we were roving. However, because we can control both the wheel rotation, wheel orientation, and the suspension system, we were able to create all sorts of strange gaits out of the rover. Crab walking, inch worming, inch crabbing. We started having to invent all these different names, including turning 2 of the wheels sideways, leaving the other 2 wheels in a locked position and literally pulling forward, like scooping, then switching, scooping, switching, scooping. And we were able to pull ourselves right out of this
Swim
impossible,
out of it.
army man crawl, swim, all sorts of metaphors for it. Now, that isn't the way we want to go across surface, because that's slow. But if it's the difference between game over and you're still going, so we've been studying those 2 to have them in our back pocket should we need them. So very, very different rover than Mars rovers.
What I'm hearing is with that crabbing, you could parallel park this really well.
Really, really well.
Really well.
Around rocks and all sorts of stuff.
Yeah, I know. I've seen the test videos, and it's amazing how it can get up and get away from that, like what you call like a quicksand type of environment. Yeah.
And this is always a trade from an engineering point of view. Having something as sophisticated as we're describing here, well, that's awesome, lots of capability. But something as sophisticated as that also means there's a lot more opportunity for things to go wrong. So there's this tension on the engineering side between keep it as simple as you possibly can, because less can go wrong, but simple can mean you can't survive challenges as well. So where's that balance between the 2? And that's what we're hoping we struck in our design of the rover.
Yeah, and one of the concerns early on we had was that there would be this very fluffy, unconsolidated soil in permanently shadowed regions, and there's evidence for it. We don't know exactly how deep it is or how fluffy it is, and that's one of actually the things VIPER will provide information for. That's actually really important. For example, if Artemis astronauts are going into a permanently shadowed region, I think they'd like to know if they're going to, foot's going to sink in 10 centimeters or 20. But because of that, as Dan was describing, we had to go with this. We felt compelled to go with a more capable system so we could get out of those tricky spots. Yeah.
I remember early on when we were consulting, honestly, global experts on the moon about what's the environment we're going to have to design this thing around. And I remember these were early days, right? Yeah. And we literally had, respected individuals who told us everything from it's going to be the softest, downiest talc, like when you unzip your beanbag and it just fluffs all over. It's going to be that, and you're going to sink as soon as you go in. And there's some LCROSS impact data that kind of indicates that might well be the case. And then other people are saying, it's so cold there, it's going to be cemented, and you're going to be skating across it. It's going to be so hard, you won't be able to get any traction. And we're sitting there going, what are we designing?
Big design space.
Yeah, it's like back to the 1960s again, when we weren't even sure that humans could walk on the moon, and we had to send surveyor, right?
Yes.
Yeah. So this is, and that's sort of what's I've noticed that this is really an exploration style program as well as a science program. It's doing the groundwork that's going to be required for Artemis. And that sort of is distinct from, say, Mars rovers, right?
Yes, very much so. And it's we work closely with our Artemis program and individuals on the, I work closely with them directly for site analysis. We really did want to provide whatever information we could to help future robotic and human exploration to the South Pole of the Moon. So I mentioned we were looking for water and we're exploring and understand the environment, but it's that the environment is almost as important as the compositional mapping we're doing. What is the geotechnical strength of the soil? What are the temperatures? How do they vary from place to place? Even just the communications. There's a potential risks of what's called multipath. When you're talking to the Earth and the Earth is way low on the horizon, your radio beam's interfering with that soil, interacting with the soil on its way to the Earth and back. And depending on the properties of the soil, you can get loss of signal strength. We've got models of this. We think they're right. It's a concern for us, but even VIPER will be able to validate those models, which will be important to any future exploration of the poles.
Awesome. Well, let's take a look at the clean room here. We see a lot of action. For those who are just joining, can you please give us a recap of what the team is doing this week?
Yeah, so this week we're finishing up the final MLI, that multi-layer installations, in preparation for ultimately those solar arrays going on that you can see all around the sides of this model here. And then what's basically the final step, which is those wheels, those 20-inch wheels that
Don't
have been
forget the
waiting
wheels.
around. I've had people come up to me and say, it ain't a rover till it has wheels, which is a fair comment, but they also are the most extraneous, most external objects, so they go on last. And as I indicated before, that's going to be in the May time frame under the current schedule. But for those who've been following along, you've been able to see this slow buildup, the onion that Tony was talking about, starting from just a chassis, a horizontal chassis, which is at the base of it, put in the batteries. The batteries are nice and low for a low center of gravity, and then building up what we call the warm box. And the warm box, again aptly named, is a box in the very center of the rover where all the sensitive electronics are located, if they can be, because it's well-conditioned, good temperatures for them to exist. It makes it easier for us to design a system that doesn't have every instrument have to be able to tolerate the lunar environment. That's very, very hard. Well, what if we could make a non-lunar environment inside this box and then put our electronics in there? So that's what that exists for, and then that's wrapped in MLI. So it's a nice little, drink cooler in there that's keeping a good temperature range in there. Then you have some of the more mechanical, external thermal equipment required to condition that space in there. And then what you're seeing out here now is the nearly done rover, the final outer MLI, and the solar arrays are going to go on top. You see those white panels along the top, the 4 panels that are silver on this model. Those are the radiators, and so those can get rid of heat when we need to get rid of heat, or they can be turned off and not release heat when we're in, for example, a very cold environment. Of course, you see in the center on the feed there, you see that's the chimney cap, as we call it, for the drill that goes right through the center of the rover. And that was installed a few weeks back, and we had the whole system on a scissor lift, went way up high, and we were able to fully extend the drill as if it were going into the soil. All went amazingly well there. And then looking at the face, you're basically looking at the face of the rover. You can see the neutron spectrometer system hanging off the front. That's kind of our divining rod that's looking down and helping us see what we think is happening under the soil, make judgments about where we want to drill, and so forth. 2 eyeballs up top, those cameras, stereo cameras, and then just on the outside of each of those, which is right here and here, are the first roving headlights that'll be going to the moon, and then the high gain antenna up on top of that. So we're getting there.
How many parts does the rover have?
How many parts? Oh my gosh. So it's a few thousand, and that's as far as I'm going to go. Because I don't know if you mean fasteners and everything else, but I tell you, we have been looking at CAD models of this rover for years. And you think, well, yeah, I know what this is like. And then you go and see it, and your mind is just blown, first by its size. And for those who've been watching the feed, you're used to it. You go, okay, so it's 1.5 humans high, 2 humans high, something like that. But I'm telling you, you've been watching it as CAD files, and then you see this. And then the one that really gets me, I can't remember which of you said, the exploded view stuff, I think you did, Tony, of all the wires when you're first putting it in. That's just the cables and harnesses that the rover needs to exist. It's nervous system, right? So to speak. Sorry, I also got a nervous instrument.
Yeah.
But then that's not even including all the temperature sensors and all that are used, that are embedded in the rover and will actually be abandoned in the rover to be able to monitor temperatures when we do that environmental test. So it's even worse than that. There's so much going on. I'm completely impressed.
Yeah.
Honestly.
But you were talking about the nervous system, and inside that hot box, warm box, that's where the computer is going to be. And everybody has computers in their pockets. What have you got in your pocket for VIPER?
Yeah. So what VIPER tried to do, and we have another tension. Like I was talking about tension between complexity and simplicity and capability. The other tension is, do you want to invent a bunch of new stuff that's maybe bleeding edge technology and go ahead and apply it here, but maybe you don't have as much comfort that it's actually going to behave the way you think. You don't have a lot of these where the system design was matured. So in our case, we ended up going with a good old tried and true 1990s era RAD 750 processor there, which will work. Now, could you run circles around it with other processors? The answer is yes.
My watch is faster than it.
That's probably true. But it's reliable and understood in the harsh environments of vacuum, of space, of radiation. Its behavior in the presence of adversity is known and understood. And that's worth more than anything else when we're already in a ridiculously harsh environment. Let's keep the variables as understood as possible.
Where we can, And this is one of the reasons we could do that was the proximity of the moon to the Earth, is we can communicate with this in near real time, about 7 to 10 seconds with all the network delays. But that allowed us to do the hard processing, the heavy processing on a real machine here on a RAD 750 here on Earth.
Right, so the proximity isn't just round trip time, but also just the bandwidth you can get back. And if you can send more data back, you can do more processing on the ground.
Exactly. So actually the two cameras are used to make stereo images, and that's how we understand the hazards in front of us. We can get a three-dimensional picture of a crater or a rock or whatever and understand its size and shape. All that processing of those two images is done on the ground. So the only and what's sent down from the cameras to make that is called a slog. It's a very, very, very highly compressed 1 and 0, basically 2-bit image that you look at and you go, I kind of can make sense of this, but it's perfect for doing stereo reconstruction. We can get those down quick, and then they can quickly, on the ground with high capacity processing, turn it into a hazard map, we call it, for the rover drivers to look at.
That's my next question. Like, what is the role of the scientists once they get that data here back on Earth?
Sure, and well, it's again, because we can operate the rover in real time, we can conduct science in real time.
Right.
And this is very different from pretty much any other robotic mission that's ever done. And the closest analog, which is not even that close, is the Apollo missions, where scientists worked with the astronauts in near real time to conduct science. I mean, the ultimate real-time scientist was, of course, Jack Schmitt, who was a scientist on the moon. So we're not quite as good as that, but what we've done is we've actually integrated from the very get-go science and scientists into the mission and into the mission operations. So there's a drive team. The drive team consists of a rover driver and a rover co-driver. Rover driver is the one who's sending the actual commands, telling the rover where to go, what speed to go, where to take images. Co-driver assists and helps and does a lot of the paperwork, if you will, to allow the rover driver to keep their focus. Then there's a navigator, tells us where we are. And then just to the left, though, sitting just to the left of the rover driver, is a scientist called a real-time scientist. They are part of the drive team. That person works directly with the driver to drive the rover. So really, it is science driving the rover. And that's very unique compared to other missions. Right next to that real-time scientist is a science lead, a role called science lead. That science lead is actually coordinating the science there with the drive team, with an entire science team that's in the Mission Science Center. And in the Mission Science Center, you have instrument scientists, you have science theme leads, so environments, composition are a couple of our science theme leads. They're processing the data in real time to actually do things like create prospectivity maps in real time. A prospectivity map, I love saying that word, is just, it's a map that a resource exploration scientist would make that tells you what's the probability of finding water in this spot. So actually we've got one already made from the data we have, and that will get updated in real time as we get real data in real time. We can use that then to guide where the rover goes, where the rover drills, and that's the role of the science team. They're on, just like the rover operators are on 24/7 while we're in communications, working 3 shifts. So yeah, the science team is working hand in hand with all the other operators to make this come together and optimize, really optimize the discovery and the return of science.
And picture all of that happening against the reality of the shadows moving across the surface for nominally a 2-week period before Earth sets, and we can no longer drive the rover because we can't communicate with the rover from Earth. There's yet another tension that's established there. So Tony and team are going through and they're executing this mission. Let's say there's a wonderful surprise, like an, oh my God, we didn't think that would happen. What do you do?
Yeah.
You probably want to deviate from your original plan because this is a new discovery. But the clock is still ticking. You got to get to that safe haven before you run out of time. So live, in the way Tony's described, we've got to figure out, oh, let's change that plan, let's do a little more of this here, let's take a note of that, then we got to run for the hill to go get into the sun before Earth sets. This is going to be throughout the mission.
Yeah, timelining and planning are at the heart of all that. So there's, in the Mission Science Center, there's a timeliner who works with a timeliner who's in the Mission Control Center upstairs with rover drivers. And they are constantly looking at that clock, you know. They're like, okay, what tasks do we have? What tasks have we completed? And then all of a sudden the science lead might come up based on consultation with the science team downstairs at the MSC, the Mission Science Center. Discovery, we just saw something, we have to stop here and you know, take a panorama. That all has to happen in real time and quickly with the timelining team say, okay, we were going to have 15 minutes delay here. How does that impact our getting to a safe haven? Do we have to make up 15 minutes somewhere else, or are we good? Do we have margin? So that's happening in a constant churn when we're operating on the surface.
So I mean, for communications, presume you're using the Deep Space Network then?
Yes.
So does that mean your planning has to account for the fact that Australia is further south and therefore you might get better connectivity for some times where you can't get scopes in the northern hemisphere? Or?
It definitely plans for each of the DSN stations. There will be often there isn't continuous overlap between them. There's known dropouts. There's scheduled dropouts. Those are all worked into the plan and constantly managed. And then there's planned margin for the that DSN station's down unplanned for any number of reasons, or James Webb had an emergency and is grabbing all the DSN. So yeah.
This is a hot topic at the moment. Like within team, this is a really hot topic at the moment, which is for the planned stuff that Tony was just referring about. We build in contingency into our design so that we can work around scheduled outages. But we don't get to just come in and say, everyone else turn off, it's all about VIPER for the next 2 weeks. But the unplanned ones, you can imagine that if we are in a sunny area and shadows are far away and we lose communications, maybe not a terrible big deal. If we're in the middle of a PSR and we are just shedding heat like crazy, we're doing work and all this, and we lose communications, that's a really big deal. So we have to work through different criticalities of our actions and try to establish prioritizations with DSN therein to make sure that our risks are contained.
And you mentioned, how each of the DSN stations are in a different position on Earth, and that really does matter, especially for the PSR case, because when we're in PSR, the Earth tends to be closest to the horizon as well, only a degree or two above the horizon. And so actually in the plan, when we're in a PSR, we have what are called horizon checks, where we take the cameras, the mast, and we go and we actually take a picture of Earth with the horizon in it, and we have a tool that automatically draws where we think the horizon should be if we are where we're supposed to be. And we do that probably about 6-7 times while in a PSR for this reason, because we are so nervous that we're going to lose sight of that Earth. in a PSR, so we're constantly looking over our shoulder. You're still there? Yeah. Okay. You're still there? Yeah.
We had really hoped during the original resource prospector days, which was the predecessor to the VIPER construct, that we could rely on an orbiting comm relay. That there would be something overhead or some string of things overhead. Because, think about it, we don't have to worry about this low horizon Earth access thing and reflections coming off the surface. We could beam up. We maybe have to be a little faster because it might be a fast passing asset or something, but we can go to them, and we could pump a lot more data over it too, because it's right there as opposed to Earth way back over there. And it hasn't come to be, so VIPER has to behave talking directly to Earth all the way through. Future missions will likely have the benefit of having a relay comm asset up there and be able to be less constrained than we are on this mission.
Yeah.
Well, we have a few more questions and comments here. This is a fun one. I love you nerds so much. Thanks for letting us see these super cool things. Why is this being done in a clean room? Maybe you can give us a little background on what a clean room is.
I can take a stab at that. So a clean room is a clean room. It's meant to keep particulate, the concentration of particulates like dust, down to a certain number per, say, cubic foot, and that's how they do that. And it's also meant to keep the humidity at just the right sweet spot, temperatures controlled, so it's all very controlled. Why do you want to keep it clean? Particulates can affect the way things operate. Any dust on that MLI or the radiators on top will change how it behaves and operates. Particulates can get into electrical harnessing and create problems there, either short circuits or disconnects. But also from a science perspective, a lot of the things we're looking for on the moon, our observations can be contaminated by dust or other things. And really, the biggest worry or the biggest thing you're getting in a clean room is human shedding.
Yeah,
and that's why they got all
stuff,
these hats and gloves and booties on. It's a large source of that particulates, and that contains water, carbon, nitrogen, all the kinds of things we're actually interested in seeing on the moon. So we don't want to go up there and say, oh wow, well look at all this wonderful things we're seeing, and actually we're staring at some human hair.
We brought it.
We brought it, exactly. So yeah, that's why we build it in a clean room. And there's different levels of cleanliness. People may have seen some clean rooms, like where they manufacture silicon chips for computer devices or for circuit boards. They can be in full head to toe garb, totally sealed off, because it's very, very sensitive to any kind of particulate contamination there.
That is an interesting question, right? Because we're going to a very filthy place.
Yeah.
So
Why
why are we
keep it
spending
clean
so much
now?
time being clean? And we just want to get it all hermetically sealed, and then then we know what we have, and then the environment's going to do whatever it does, but we're sealed up.
Yep.
Another viewer is asking, does VIPER have any tip-over recovery or protection?
BattleBots thing. Yes. Yeah, we have an arm that flips out and we flip over all 1,000 pounds.
Yeah. How low is the center of mass on this?
It's very low. It's deceivingly low. You look at this and it looks like a very tall, well, it is a very tall rover to the top of the mast. It's like 2.5 meters. But that's deceiving. There's a lot of air and the warm box and all that.
Emptiness there, yeah.
The batteries are heavy. The batteries are you can't see, but the batteries are way down at the bottom. So it has a good CG design, center of gravity design, despite how it might appear just from the outside.
Well, you want it to be tall so that you can get the solar panels above the ground clutter.
There's again more of these competing, for all you engineers out there, all these competing interests that you have to trade against. But yeah, so it's got defined requirements for what we can climb, the height, angle that we can climb. That includes going down on ramps. We've even had to do combined constraints, like if we're going down the lander ramps, but then on top of that, One of the lander ramps is in a crater, a little mini crater. So now they're splayed. And so you've got rolling components and tipping components. Again, this design of the suspension system, though, can really help us out. When we've run these practice runs going down the ramps, instead of just rolling down like this, where our rover body matches the angle of the ramps, we actually can push the front end up and drop the back end and actually go down the ramp at an angle like this because of that capability. Again, complexity working in our favor as long as it works.
Yeah, and I've seen some of those egress tests and how, you know, it started to move from side to side. So you guys done a lot of testing as well.
Yes.
Let's see. How long are you expecting the rover to last?
The mission durations we're looking at are about 100 Earth days long. With about 50% of that, it's sitting in a nice sunny spot while we're out of communication with it. Total traverse distances, as I mentioned earlier, are about 30 kilometers or so, with maybe 30 science stations and 30 science stations, something like that, and maybe even up to 50 drilling activities. So it's going to be a busy rover. Ultimately, what happens is we're going to the South Pole in the South Pole summer. So the sun is the highest it is, you know, a whole 6 degrees above the surface. But eventually, as we move out of summer and into fall in the South Pole, at the South Pole, these shadows just become too large and too all-encompassing, and we'll go into a deep, deep freeze for until the next summer comes up. But it's not designed to survive a long, dark shadow period. It's only designed to survive about 50 hours.
Okay.
Now, functionally, this summer that you're talking about is a period for the South Pole currently that's roughly around September, October of any given year through, say, March, February, March of any given year. And that moves slightly year to year. But that's the window where the rover can get enough sun and have communications back to Earth to work. So one of the struggles we have is over that span, if you launch late, it doesn't slide around to the right. The back end constraint's still the back end constraint. So every day that you're foreshortening the front end, the shorter your mission, the less distance, the less places we go to, the lower the science value because we're simply getting less data. So there's a point where if you're sliding the launch date or arrival date enough, is it worth it anymore, even though you may still have some days? And so this is why we're interested in arriving at the beginning of what Tony called the summer, the beginning of that good lighting condition period, to get as much opportunity as we can out of it until the inevitable everything falls into darkness and game over. We're all done.
And we've had a lot of conversations and not made a decision about how that ending will come. There's talks about driving it into a PSR. It goes deep and as far as we can until we run out of battery. So then we're entombed at minus 220 degrees below zero. Or we actually make a run for another safe haven that's nearby and try to go one more day. But what we're doing there is we're just driving it with reckless abandon at that point. Just go. And we haven't yet decided how that's going to play out.
Awesome. Do you have any other questions, Scott?
Well, I mean, that's already talking about the end of the rover. Wow. But I mean, so you have some, what I'm hearing is you have some constraint. If there's delays, there'll be a point where you say, got to wait until next year to really maximize the science value. And you've probably got planned, some idea when that is.
This,
Yep.
oh, sorry.
Nope.
Well, this mission, it costs a certain amount of money, and it's designed to get all the questions we need answered robustly in that window.
Yeah.
So the idea of trying to hang on and pick up the next summer's window to resume it, somehow park it in a nice spot. I don't know that there's a nice spot that can make it through the winter, but it's not in play. So therefore, it's all about that window. What can you get done?
Yeah.
And when we're going into the PSRs that Tony was talking about, all the PSRs through day 1, 2, 3, 4, they have to be ones we can get out of, or otherwise it's the end of mission. But that last one that you were referring to, that's the first PSR we could go into where we're like, I don't need to ever get out of here. So let me just go
relaxing.
Thelma and Louise, just head in there and just get as much data as we can until batteries die.
But yeah, I did hear you talk about LCROSS, because that's a relevant mission. You guys, and you worked on this, right?
Yeah, Tony and I both did.
Yeah, so LCROSS, I love that mission because it is, slamming a rocket into the moon to see what it does. I'd love you to tell me more about your experience.
Yeah, what did our center director call it at the time? A precision-guided bombing run of the moon, which is completely false, but it feels good.
It's not a space station, it's a moon.
Yeah, and so this was back in 2009, and it was set up to try to answer that fundamental question of all those elevated hydrogen signals down in the polar regions, north and south. Could that be, is it just elemental hydrogen or entrained in the soil, or could it actually be bound water ice? So this was a really big deal to at least answer that binary question. And so LCROSS did with vigor. We landed with vigor and confirmed water ice. You could talk to that.
Right. Yeah. So it was designed. It was a really spectacular use of an opportunity too, and that's something I'll mention real quick. Is the original launch was just for the Lunar Reconnaissance Orbiter, and which is still in orbit now and still taking great data now. But they had to upgrade the launch vehicle. There was an issue with the delta nutation of the tanks. I think that wasn't going to work with it, so they had to go. Is that about right?
I don't know. I have to dig into that.
Okay. Anyways, they upgraded the launch vehicle and had an extra 1,000 kilograms then that they could send to the moon, and they didn't want to not use that. They're paying for it. They being NASA, so they sent out a proposal to the NASA centers and the labs like JPL and said, what could you do with 1,000 kilograms? And so lots of people working different ideas. Dan and I were working different ideas together. One of the idea for LCROSS came up with some colleagues at Northrop Grumman and here at Ames, Jeff Briggs, who's now since retired, said, well, hey, we're talking about impacts already. You could bring an impactor. And then we were talking about, well, you could just impact the Centaur. And then it came together like, wait, you could use that 1,000 kilograms to build a spacecraft that got up close and literally flew through the debris cloud from the impactor and use the Centaur. So I like to think of it as we got, for a price of 1,000 kilograms, we got really a Centaur, which was 2,500 kilograms, and 1,000 kilograms. So we got 3,500 kilograms for a price of 1,000 out of it. But that was key because we were able to use this large impactor on a very unique orbit, strike very vertically into the south pole of the moon. And then we had what was the shepherding spacecraft. That's the one that actually brought the Centaur to the moon, launched it, or really just released it at the moon. But it was able to then fly with all of its instruments right at the impact. It slowed itself down, so it's 4 minutes behind the impactor. And then the Centaur impacted. It continued observing all the way down until it flew through the plume and impacted itself. And so actually I mentioned real-time operations with VIPER on LCROSS because, again, it was a real-time, we could communicate. It was a lunar mission. That was actually the first real-time operations. It was us, as we were going and getting close to the moon, we had a particular camera set that we thought we could image the surface of the crater we're going into. Cabeus is the name of it. Is in permanent shadow, but we said, hey, if we go to a different exposure on this camera when we're close enough, I bet we can see the floor. And so we're at 2 minutes after impact, we're going in, and we've got a plan, and I call out, let's go ahead. I talked to the payload scientist, let's go to exposure on this camera. And she called out to the payload operator, yes, go to, it was near infrared 3. So it was NIR2, go to exposure 300, say. And so she calls it over the loop, NIR2, exposure 300. And the payload operator comes back and says, copy MIR2, because we had mid-infrared cameras too. MIR2, exposure 300. She's like, no, NIR2, exposure 3, copy, MIR2, exposure. No, November. Meanwhile, I'm just sitting there going, oh my God, we're going to miss it. Yeah, they got it in, and it was the first pictures of the Florida cabeas ever taken, and it showed us the crater that we made.
Amazing.
So what we saw in that ejecta cloud was water ice, but also carbon dioxide, hydrogen sulfide, methane, ammonia,
Gold, silver,
platinum, potassium, mercury,
And
all kinds of wonderful
we're very
stuff.
careful to make sure all those stuff wasn't from the Centaur that you just slammed into the moon.
Exactly. We did a bunch of venting of the spacecraft, first of all, the Centaur, and then we did what we call barbecue rolls to heat it up evenly all around so all the vapors and stuff would outgas. We monitored that. On our way to the moon was about 110 days, so it was a nice long period of time for all that stuff to outgas. And then we also had a material inventory that we could check against and say, okay, I saw this much gold. How much gold is actually in the bells? They use gold in various places, and no, there's way more gold that we saw estimated than could have come from the Centaur.
So we didn't
itself.
bring it. Yeah.
We didn't bring
all that in.
We didn't bring all that. Yeah, and that was a really important factor that had to get worked into all of this. Using an upper stage as an impactor is not a usual thing. So
It's what you had to work with, right?
Yeah. Well, the people who selected us, the selecting officials, said that was what got the selection, because there were this was a competition of 13 different proposals, and we ended up coming up on top, and there were other impactors, but they built in an impactor into their 1,000 kilogram, and we, Captain Kirk Kobayashi Maru'd it. We totally cheated and used this thing that should be out of bounds, but why not?
It didn't say we couldn't.
Yeah, I didn't say we couldn't.
Right.
And then, got much bigger of a mission, as Stanley said.
And so now VIPER is going back to look at the same region, look at that water, and look at it, instead of one big signal, it's there. You're now going to be looking at where is it, how deep is it, what's its properties. This is what VIPER's about.
And exactly, and the LCROSS impact was a very coarse measurement, meaning it sampled a 30 meter or so 20 meter wide chunk of dirt, the crater, and it's critical though to actually confirm, as Dan said, what we thought we were seeing in the orbital data. But VIPER will very methodically map out the compositions at scales, what I call the human scale. So if we want to get to the moon and actually utilize water or other volatiles that could be there as a resource, we can't understand it on a kind of a 20 or 30 or 40 kilometer scale. We have to understand it at the scale we'll be working at, which is the human scale. And so that's actually in part what defined the distances we're driving and the types of measurements we're making and how we're making them, so that we can actually provide some kind of predictive capability to say, hey, if you dug that 20 by 20 meter patch of dirt over there, you'll get this much water and this much this and this much that.
Awesome. So we're kind of near our end of the live stream, so this is a great opportunity to send more questions and comments to our VIPER mission experts. And for those that are just joining, we're looking at the clean room where NASA's moon rover is being built. Can you give us a recap of what we're seeing right now? What is the team working on?
Dan?
Yeah, so that's quite a team that's assembled at this point. There's quite a few people in there. So we're at the nearing the end of the build of the VIPER rover. That is an 88% complete as of a couple days ago rover. And what is happening is they're putting on some of the final MLI. You see a person there hanging, that's Emily, hanging a bunch of wires coming off of it and so forth. Part of the trick here is not just the wiring and everything that's required for the rover itself, but to do the later instrumentation when we're in environmental test. And I don't know if that's specifically what she's holding, but I know when I was there just a couple weeks ago, there is just meters and meters of this instrumentation cable there that all has to be managed. But this is the final wrap of the multi-layer insulation, which keeps the rover both clean and warm inside. And then next up, when this is done and the remaining measurements are made, the solar arrays go on, which look a lot more like the device you see here, this little model here. And then finally, the wheels, the 4 wheels that will go on as one of the very last things. And then we have a finished rover, and that begins the test campaign to then go in and put it through some environments that are analogous to the moon, and we hope it all goes perfectly. But if it's not going to go perfectly, we'd rather find that out on Earth than on the moon, where we're extremely limited in what we could do about a tough discovery.
Presumably you're also going to analyze how it behaves during the launch and the cruise to the moon, right?
Exactly. Yeah, great question. So let's talk about a thermal vacuum cycle. So when we go into this environmental test, I'm talking about system level environmental test, which means this whole system is going in there. What we do in simplest terms is we cycle between very hot temperatures, all in a vacuum of space. We try to recreate that as best we can, go up into elevated temperatures. In doing so, we're baking off any volatiles that are in there. I mean, there are humans in here breathing air and stuff, so you got to clean all that up too. Then you go down to very, very cold temperatures. You might sit and dwell at each of those. What's it like? How's the rover perform sitting at a high temperature or sitting at a low temperature?
What's the cold temperature?
The cold temperature, if you're going into a PSR, could be as cold as negative 400 degrees Fahrenheit.
Wow.
On one end. And yet the high end is kind of a nice day here on Earth, mid 70s to 80 degrees Fahrenheit. And you've got to have a system that can handle all of that, which is a challenge. But to your question specifically, not only would you do these cyclically, but you could shape the curve of how you do them so they are mimicking some behavior on the moon or during launch.
Yep.
And so, for example, if you start at a high temperature and figure out your slope going down towards cold temperatures, that could be made analogous to launch, where you're starting at the warm temperature on the launch pad. Even if it's a cold day, it's the warmest it's ever going to be. And then it's going to launch and get into colder and colder environments in a vacuum through all these environments. And so we can replicate that as best we can to try to make sure this rover can survive that tough environment. Many people may not know this, but many times spacecraft, not just this rover, their hardest design criteria is to survive launch, not to actually do the mission, but to get off of Earth. That actually becomes the design constraint, which blows my mind.
With a lot of vibration, acceleration, and you've got this pressure that's dropping over a minute, and things sometimes break just because of the pressure. The gas is flowing out.
Absolutely. It's a tough environment.
And the flight then from the Earth to the moon, which takes about 5 days, and then they will go into lunar orbit just before landing. There's a lot of conditioning then still of the rover that's taking place. We have heaters that go on and do what we call a bake out, because one of the things you cannot get away from on Earth is water. It's everywhere, and it sticks to everything. And at the kinds of levels of concentrations we're trying to measure on the moon, it's even the water that's sticking to the aluminum metal is significant enough for us. So what we do actually, after we get out of this wet planet, we get into hard vacuum of space. We heat up as certain critical components, like the instruments, as much as possible to drive all that water off. And we do that for pretty much the entire ride to the moon, so that when we land on the moon, we're desiccated as much as we can be, so that when we roll off, again, we're measuring in situ water, not water we brought from home.
So do you anticipate, here's an interesting thing, the lander is going to use rocket propellant, and one of the exhaust components is going to be water, so you probably have to figure out how to not measure that.
We intend to measure it.
Right.
Because then we know, and actually that, you bring up a fantastic point, which is given us a lot, we've given it a lot of thought, because it could give us a lot of heartache. We've worked with the lander provider to understand the total mass of exhaust, when it's coming out, the rate it's coming out, and we have members on our science team who are experts on modeling that and understanding that, and have published on it. But we also did things like exclude areas of our mission area from landing. So our landing site had requirements that said you cannot be within 800 meters of these permanently shadowed regions, because we wanted to minimize the contamination there. So we will drive out of our contaminated region. And this is what I meant by we want to measure it. I hope to see water and other nitrogen compounds that come out of that exhaust at and around the lander, and then watch them as they fall off as we get further and further away. Exactly right. Yeah, because that will give us that confidence that we are really seeing what we intended to see. But it goes further. There was actually some discussion of Intuitive Machines' recent landing. Mm-hmm. They were going to land in an area near our mission area. And the Commercial Land and Payload Services contacted said, do you have a concern with that? And I said, yeah, I do, I really do. Because they don't, and so we actually worked with them, and now we've defined with the CLPS office and broader NASA a VIPER keep-out zone that landers, we can communicate, if you land within this region, it could potentially impact our results.
What about like a braking burn over that region? Is that
that counts?
Counts.
That's actually sometimes the worst. Yeah. So, so it's not just a flood. It's a no-fly zone that extends into space.
And so your required landing precision for this is going to be what?
Plus or minus 100 meters.
Plus or minus 100 meters.
Yeah, radius of 100 meters, and that's mostly defined by really doing analysis of the roughness of the terrain that we're landing in. There's this much. These are the slopes, these are the craters, and if you get much larger than that, it's really hard to find a place that is, say, 90% free of hazard. So there's that, but there's also, we don't want to land so far away from where we intend to drive that we spend way too much time driving to where we want to explore. Mm-hmm. So precision landing is key, for sure, in future missions.
Oh, we'll take a few more questions here from our audience. There's one here. How will VIPER send its data back to Earth?
So we had discussed earlier that we don't have the benefit of a ComSat, a communications satellite that's in orbit around the moon. And so that means we have to, with this high gain antenna here, and if needed, this lower gain omnidirectional antenna, send it directly to Earth. And when you heard earlier that Earth is going to be pretty low on the horizon, as Sun is also going to be very low on the horizon, it means we're shooting our signals directly, almost horizontally, tangentially across the surface to the moon. So we actually designed our communication system to have some extra power behind it to be able to blast through any of the reflections we might get shooting that close to a reflective surface. And by the way, this isn't new for us. Going way back, maritime periods before we had GPS satellites or other communication satellites, ships on the ocean, just on Earth, would have trouble doing ship-to-ship because of the exact same principles, reflections coming off of the ocean. So this is a pretty well understood problem. The problem is it's not very well understood on the moon and the exact nature of regolith, moon dirt, and exactly how it's going to reflect back to us. So our solution is, since we can't know the answer in advance, we're just going to power through it, and we brought extra juice to be able to blast through it.
I'm just looking at this. This is a phased array antenna on here, and it rotates independently of the lights and cameras underneath it, right?
Yeah, there's a pan-tilt system down here which separately controls the stereo cameras and then rigidly connected to the lights, and then completely independently in all the degrees of freedom, the comm system that can point back to Earth.
And so what kind of data rates do you get?
Well, we for science planning, we are allotted about 250 kbits per second. But I think that's, again, engineering built-in conservatism into that number. So I've seen numbers as high as a megabit per second. And that's what we actually had on LCROSS, was a megabit per second.
With the big dish.
With the big dish.
You didn't have long to send data back on
that.
No.
That had to come back right away. Yeah, that's a great point. Is a lot of the images from the rover can be stored on board, but they generally are downlinked immediately because they're used to decide where to drive next. The science team can take uncompressed, really high resolution images. Those can stay on the rover a longer time, and then the Nervous instrument has a high resolution imager. That all can add up to a lot of data, and even at a megabit per second, it can take a long time to get to the ground. But just like here on Earth, in space, memory is cheap. So we have a lot of memory on the rover, and then there's times when we park and we're not generating a lot of imagery. We're downlinking all that data. So just before we go into a safe haven and park it and put up.
Or after dip 1 of a PSR, we're just sitting there toasting up and getting power positive.
Getting power positive, it's like downlink all the data you got backed up.
So this is like solid state flash memory, I guess, like we have on our phones.
Yeah.
And a final question from our viewer. What questions are you most looking forward to answer based on the data that will be received?
Oh, boy. So I could, how much time do we have? No. One of the most fundamental questions in my mind is, where did the water on the moon come from? We know there's water there. The LCROSS mission showed it. Other subsequent missions and data sets actually taken even before LCROSS, people went back to and looked at it and said, oh yeah, there's water. We see it all over the moon in just different concentrations and maybe some different forms of it, meaning is it hydroxyl, or is it bound to the grains, or is it ice grains? Where does the water come from? We still don't have 100% or even a 50% certainty on that, and VIPER can address that. We can look at the relative abundances, even if we find very, very small amounts of water, we can compare it to other volatiles we see, and that will help us understand, did it come from early volcanism? The mass spectrometer, M-SOLO, can look at the isotopes of water and say, hey, the isotopes, basically the different masses of water with at the nuclear level having a little bit more mass. But isotopes are excellent fingerprints for actually the origin of water. Cometary water has a little bit different isotopes than terrestrial ocean water versus asteroid water. So there's a lot of ways we can look at that problem. And I think that's going to be a huge, really big impact overall scientifically, because it's not just the moon we're talking about. The moon's our closest neighbor, but we also have that also actually is input into where the Earth's water came from, and then the water on Mars as well. So it's actually, once we answer that question, it actually has impact to the entire inner solar system.
I think this is the beauty of the mission, because everything you just heard Tony say was very science-centric, big questions that this could help to answer and all that. And that's worth it all by itself. And then there's the other part, which is the exploration side, which is the utilization of whatever it is that we end up finding, and how you utilize it, and the tech that needs to be matured in order to go about getting it. Right. Both of these coexist in that mission. And so what we like as project people is, as one thing becomes a little more important than the other, and maybe it moves, and that happens. We've both worked at NASA more than 30 years. That happens. But VIPER's the answer. And so that's really the beauty of this. I think the commercials that are going to come in with the answers that VIPER is going to provide, even if they're different than we expect, it doesn't matter. It's the truth teller.
Exactly.
Right? It's going to tell us what's going on, no matter what we thought in advance. And then some commercial tech developer people are going to be bummed by what we discover, because they thought all the water ice was going to be a meter down, and they've got this killer way to go get it. But guess what? Turns out the most economical way to get it's in the first 20 centimeters, say. Okay, well, that's a different type of technology and approach that you would take. So I just love the idea that this truth teller is going to give us those answers, and then everything stands on its shoulders.
Yeah, it's a cornerstone for everything that comes after it, for sure.
I love it, truth teller.
Yeah.
So do you have any final questions?
There's one other sci-fi trope, and that is helium-3 on the moon, and you guys are actually going to have gear that will be able to quantify that to a certain extent?
No, we won't be able to look for,
The M-SOLO should at least
It can. It also uses helium as a calibration gas.
But helium-3 is different.
It is different. So, yes, we can measure down to helium-3.
So you get some signal, even if it's not a perfect, pure...
If it comes off as gas, and we see that, I'd be surprised where we're going. But we're going, I always like to say, we're going into this with our eyes wide open. There's so much we don't know that we won't discount anything. And
the other question is, what kind of awesome pictures of the Earth above the moon can you get from these cameras?
They're going to be, the navigation cameras are quite good. They're large field of view because they're meant for driving, right? They're not color. They're actually monochromatic, but they actually have a very narrow blue filter on them. Our headlights are 460 nanometers, which is blue.
Very blue.
Very blue. So we'll be able to take a picture of the Earth in a black and white sense, but they will be very high resolution. What's really going to be fantastic is we're going to see it through all of its phases, you know, and so we'll see a crescent. We have this incredible simulator. How we practice driving the rover is it's an awesome game. It's a simulator that simulates the terrain as high with as much fidelity as we can possibly imagine putting into it. It simulates the phase and the position of the Earth as a function of time. And we were doing a practice sim the other day. We're going to do a PSR. We are in total darkness in the PSR. We're doing this horizon check, look over there, take a picture, and it's this beautiful crescent Earth over a lit ridge. So we're in darkness, but in the distance there's a lit ridge that you could see, and it was just a phenomenal simulated image. So I can only imagine what it's really going to look like.
So are there conditions where Earthshine may actually help you?
Yes.
Yeah.
Yep. Earthshine, we will definitely be doing those experiments, taking pictures in the dark without our headlights. Is definitely on the list of things to do. It might actually be the easiest way to drive. You can imagine, you know, the headlights are great, but anytime you try to take a photo with like a headlight or a flashlight, it doesn't make a very nice picture. We've actually, in the simulator, we practice this, but we will definitely do it on the mission, is actually image in the dark and say, hey, there's enough scattered light and earthshine that, well, let's actually go with a longer exposure and just drive that way.
Wow. Amazing. And I want to know, what's your favorite part of your job? What do you enjoy most?
It's got to be the meetings.
Love them.
Especially the long ones.
So I love instrumentation and hardware. So I'm a scientist, but having an idea of how to make a measurement, seeing that develop over time and then actually occur, like on the moon, is absolutely the most fulfilling thing, and to me, professionally speaking, being able to have that part of you actually reach out beyond Earth and in a way, you know, touch the thing it is you're trying to understand. So that's what I like most.
How about you, Dan?
I kind of tipped my hand earlier. The idea, think how few people get to be anywhere near a mission of any type. Now narrow that further. How many people get to do a lunar mission? Now narrow it further. How many get to do, in Tony in my case, a orbital impactor mission and then follow it up with a roving mission? This is getting to be a very small group of people of all humanity. That's an honor.
That's amazing.
And we take that very seriously. It's honestly helpful and wonderful for us to be able to chat with folks and tell that story, because honestly it reminds us in between all those meetings.
Well, that's just it. It's a job, right? And you have to step back sometimes and say, oh my God, I'm the luckiest person in the world.
And the idea of what could be built on the shoulders of this, and everything that you can imagine, times 10 that, because there's all the stuff that you haven't even figured that some other smart person is going to come along and go, well, if I take this data and that data, then I could, you're like, what? That's fantastic. And that's all in front of us for potentially decades. That's pretty cool.
Amazing. Well, thank you so much, Tony, Dan, and Scott. We had a fantastic time.
Thank you.
And thank you for everyone that submitted questions and comments. If you want to learn more about the VIPER mission, follow @NASA Ames on social media. We'll see you next time, and go VIPER.